it's a great pleasure to have Umesh Shankar from IIT Bombay. Umesh is a PhD student there, and he's gonna tell us about some enumeration results on the alternating subgroup. Take it away, Umesh.
Yeah, thank you, Stoyan. So, my talk will be titled Odds and Evens. So, we will discuss some permutation statistics for the alternating subgroup. So, okay, 1 second. Yeah. So, let me start out by how I want to do this talk. So, first, I'll just give a brief overview of the typical permutation statistics we will be looking at. Then I will discuss what are called signed variants of these permutation statistics. We will look at the distributions of these two statistics, especially over AN, what properties they have, like how they compare with the distribution over SN. And then we will look at some pattern avoidance like for permutations in AN. And finally, some ways to generalize this. That the questions over there are slightly open-ended. So yeah, so let me get into the talk. So I want to start by defining what are descents. So let's take a permutation. So pi1, pi2 up till pi n, it's written in a one-line notation. This is an example. So identify the positions I where pi of I is strictly greater than pi of I plus 1. So in our permutation, this will be 7 and 1, 5 and 4. So the places between them will be our descent position. So you just count the number of such positions. That will be called the descent of a permutation. So in this case, it will be 2. So the descent, as we can see, is a function that we can define on any permutation for any size. So it's a function from Sn to n for all n. So descent is an example of a permutation statistic, a map from the set union of Sn to the set of naturals. So enumerating polynomials. So let me just define what these are. So the set Sn has n factorial elements. Each of them have, each of these permutations will have a descent value between 0 and n minus 1. So let A and D be the number of permutations in Sn with D descents. For each n, so we will have an n tuple. So an0, an1, so on till an comma n minus 1. So we will encode this as a polynomial. So an of t will be defined to be some running from d equal to 0 to n minus 1, an comma d, t power d. This is also when we count each permutation, if we count t power descent of that permutation, this will match with what we are defined. So this is the famous Eulerian polynomial. So it has a lot of interesting properties. We know the generating function, we know recurrences, and this polynomial is palindromic in the sense that when you read the coefficients from the left or the right, they will read the same way. And it has only real roots, real and simple roots. So this is the list of the first 5 Eulerian polynomials. This is I've taken this off of OEIS. Thank you, Neil sir. 1 plus t, 1 plus 4t plus t squared. So the thing is, we can do this with any statistic. Once we have a statistic, we can have a stat enumerating polynomial. We will also be interested in what are signed stat enumerating polynomials. Basically, apart from t power stat of pi, we also have an additional factor of the sign of the permutation. So we want to sum over all permutations, sign of the permutation times the t power the stat of the permutation. So why stop at one variable? We can extend this to how many ever statistics we want. So if we have R statistics stat1 to stat R, then we can define so stat1 to stat R enumerating polynomial as pi belongs to Sn, t1 power stat1 of pi, t2 power stat 2 of pi, so on up till tr power stat r of pi. Similarly, we can also look at a signed variant of this, where we will additionally have a sign factor in the summation. So why do we want to study the signed enumerating polynomial? Because if we know the distribution of the statistic over the symmetric group, and we additionally know the signed variant, then adding those two will just give us 2 times the distribution of the statistic over the alternating subgroup. So this is one way in which we can get the distribution of a statistic over the alternating subgroup. Like another way, because the alternating subgroup is a normal subgroup of Sn, is we can get results for conjugacy classes and then look at the normal subgroup as a union of conjugacy classes. This is another way to get results about An. This is one common way to get results about An. So let us look at the sign descent enumerating polynomial. So sign descent enumerating numbers, like they were first studied by Lode. When studying the cyclic homology of commutative algebras, he came across a sequence of numbers and he found out that they were actually given by this particular, like, can you see my cursor? Is that visible?
Yes, we do.
Yes, we can.
Yeah. So he looked at this summation where you look at all permutations in Sn that have exactly k descents and you just count the sign of those permutations. So if you just count one instead of the sign, you will get the Eulerian number. But here you're counting the sign. So this is slightly different from the Eulerian number. However, Forta and Desarminian, they actually show something, that they are related to the descent enumerating polynomials, the Eulerian polynomial. They show that sign descent for 2n, that polynomial, which is defined in this way, is actually 1 minus t to the power n times the Eulerian, nth Eulerian polynomial. And sign descent enumerating polynomial for 2n plus 1 will be 1 minus t power n times the n plus first Eulerian polynomial. So,
Umesh, is this easy to show?
So we will look at a proof of this. Like this is Michel Vox's involutive proof of this. We will just look at that. Well, they prove it through recurrences, but yeah, this is one. So let us just look at the sign descent polynomial for n equal to 3. So 1, 2, 3 has sign 1, 0 descents. 1, 3, 2 has -1 sign and 1 descent. And all 6 I've just written down what sign they have, what descents they have. So if you just want to sum them, you'll get 1 minus t plus t plus t minus t squared. So somehow this minus t completely cancels out and you're only left with 1 minus t squared. So we can ask, is there a natural way that explains this cancellation? Is there a sign reversing involution that explains all the cancellation and explains what these terms that are left behind in the end? Is there a sign reversal involution? This was hinted at in the paper of Forta and Desarminian, and shortly after Michel Vox gave an involution. So let's take a look at that involution. So you take a permutation, pi equal to pi 1 to pi n. The same example from before. So find the smallest I such that the pair 2i minus 1 and 2i are not adjacent in the permutation. So in this permutation, it will be 3 and 4 because 1 and 2 are adjacent. So 3 and 4 are not adjacent. So this is the smallest pair such that 2i minus 1 and 2i are not adjacent. So we will just swap their positions. If such a pair exists, of course, if doesn't, like there is no such pair, then we will leave it fixed. So like this observation here is that when you flip 2i and 2i minus 1, if they are not adjacent, then the descents remain the same. But you have multiplied with one transposition, so your sign is going to change. So now we know this. Now we know that this is an involution because, like, I think that is easy to see that this is an involution. So we have to see if the fixed points are somehow corresponding to the ones that we want. And what are, like, let's describe what the fixed points under this involution are. So a barred permutation on Sn is a permutation written in one line notation along with some bars over some symbols of the permutation. So for example, 2, 1, 2, 4, 1, 5, 3 is a permutation, and I just put bars over 2 and 1. This is a barred permutation. Or I've just put a bar over 4, so 2, 4 bar 1, 5, 3 is also a barred permutation. So we can bijectively map the fixed points under the involution to these barred permutations. And barred permutations, we know that the number of barred permutations will be 2 power n times n factorial. So, like, if we look at this formula, we have that the number of terms that will be left out will be exactly that. It will be 1 minus t power n will give us 2 power n terms, and then like the nth Eulerian polynomial will give us n factorial terms. So we are expecting 2 power n times n factorial terms to be left out, and those are exactly the fixed points, number of fixed points in this. So we are good to go. So how is the bijection? So you take a barred permutation. If there is an I, you replace it by the pair 2i minus 1, 2i. And if there is an I bar, you replace it by 2i and 2i minus 1 in the reverse order. So here, like for this example, 2, 4, like bar over 1, 5 and unbarred 3. So 2 we will replace by 3, 4. 4 we will replace by 7, 8. 1 bar we will replace by 2, 1 in reverse order. And 5 bar we will replace by 10, 9. And then 3 we will replace by 5, 6. So this is a bijection. This is easily reversible. So the same thing for odd values, we will show that the fixed points are in bijection with barred permutations where the element n plus 1 is unbarred. So once again, if I is not n plus 1, replace I by 2i minus 1, 2i. We will replace I bar by 2i, 2i minus 1, and finally n plus 1, 2i plus 1. This is a bijection. So this is an example for the bijection. So this is a proof for the theorem that we saw for disharmony. This is a proof of that. So let us look at another permutation statistic. So the descent and exceedance, we have known about these permutation statistics for more than 100 years now. Like McMahon's book came out in 1915. So we've known them for at least 110 years now. So the exceedance statistic. So let's look at the definition. You take a permutation pi, which is pi 1 up to pi n. Like to calculate the exceedance, it is
the name statistic is due to Dominique Fuata. McMahon called it index. So the name, of course, you're right that it goes back to McMahon, but the terminology statistic, I think, is due to Dominique Fuata. Thank you.
So I did not know this. Thank you, sir. So for calculating exceedance, we will write the permutation in the two-line notation. So identify the positions I where pi of I is strictly greater than I. And this is the ones that are underlined. 3 is strictly greater than 1, 7 is strictly greater than 2. The number of exceedance is 2. So this is the exceedance statistic. So like this was noted by McMahon that descents and exceedance, both these statistics are equidistributed over Sn. So he showed, I'm not sure, I think he showed it through recurrence relations, but a bijective proof of that. So there's a small type, one that takes a permutations to k descents to one with k exceedances is called the first fundamental transformation. This is due to Forta. So So now let's look at the signed exceedance enumerating polynomial. So we saw the descent polynomial, we saw the signed descent enumerating polynomial. So exceedance polynomial is the same as the descent polynomial. And now we are going to look at signed exceedance enumerating polynomial. So the signed exceedance enumerating polynomial, signed exceedance numbers, like Mantachi proved this in 92. Like he gave this very simple formula for the signed exceedance polynomial. So it is just 1 minus t raised to the power n minus 1. So we will look at a sign reversing involution that gives this result. But before that, we will also look at a simple proof of this. So this proof goes to determinants. So you look at this particular matrix. So everything on and below the diagonal is 1, and everything up strictly above the diagonal is t in this matrix. So the determinant of such a matrix is given by this expression. It is sine sigma m1 sigma 1 m2 sigma 2 till mn sigma n. And by definition, mi sigma I is 1 if I is not an exceedance position, and mi sigma is t if it is. So therefore, the determinant of this matrix is exactly the signed exceedance polynomial. So this determinant can be explicitly computed. Like you can subtract the second row from the second column from the first column, and then just expand through cofactors, and you can calculate it to be 1 minus t power n. So this is a simple proof, but somehow this does not explain why this 1 minus t power n minus 1 appears. So Siva Subramanian is actually my advisor. He told me, can you like give a satisfactory sign reversing involution that does this? And he also gave me, like, he was also saying that 1 minus t power n minus 1, like the symmetric group has n minus 1 generators. So, and we also know that if you flip a generator like S1, if you just put it on some permutation, then it swaps the like positions of I and I plus 1. This is either going to change the descent, or it is going to, like, if they're in adjacent positions, it will increase the descent. But if they are not in adjacent positions, they will keep the descent same. So can you use this to somehow create a sign reversing involution? So we got a sign reversing involution like that. So this was done through what are called canonical reduced word decompositions of a permutation. So let Si be the transposition I plus 1. So we know that Sn is generated by S1, S2 up till Sn minus 1. So we will look at a canonical way to write any permutation as a product of these generators. So how do we get the canonical reduced word? So to get a permutation pi 1 up till pi n, we will start with the identity permutation. So then we will multiply the identity permutation with generators on the right. So to move pi n from position pi n to the last position. So we will move it slowly by first from like its position pi n, we will move it to pi n plus 1, then pi n plus 2, so on. Slowly we'll move it and get it to the last position. So, and whatever generators we use like this, we will keep track of them using Rn. So now we will again multiply generators and move the second last element pi n minus 1 to its correct position, which is the second last position. And then we will keep a track of what generators we use with Rn minus 1. And we will repeat this until we have reached our permutation. Because there's an example. This is just for explanation's sake. So this is an example. So we want to get the canonical reduced word decomposition of 4, 1, 5, 2, 3, this permutation. So we will start at 1, 2, 3, 4, 5, and then we will multiply with S3 and S4. So because we want 3 to go from the third position to the fifth position. So S3, if we multiply on the right, 3 will get to the fourth position. Now again we multiply S4, 3 will get to the fifth position. So we will end up with 1, 2, 4, 5, 3. So now again we will multiply by S2, S3, and now 2 will get to the correct position. Then we don't need to multiply anything. So it'll like 5 is already in the correct position, so we don't multiply anything. Then we need to multiply by S1 and we will get 4, 1, 5, 2, 3. So this is the canonical reduced word decomposition for our permutation 4, 1, 5, 2, 3. Basically, it is S3, S4, S2, S3, 1, S1, 1. We will write it in this form. And we will give a involution on canonical reduced words. So some observations that we can make. If you look at the product Rn minus 1 up till Ri, so we saw that Rn gets the last, like when we multiply by Rn for the identity, it gets the last letter matching to our permutation. So when we further multiply by Rn minus 1, it'll get the last 2 letters matching. So when we multiply all the way up till Ri, you'll get the last n minus I positions matching. So, and the second observation is that Ri will be of this particular form. It will start at some Sj and it will go unbroken till Si minus 1. Because we will take some letter, we will move it all the way to its correct position. Like because we only have adjacent transpositions in our hand, it will have to go through every position. We cannot skip positions. So this is an unbroken string. Like every index from j to I minus 1 will appear. And furthermore, it has to end with Si minus 1. Because like only if you apply Si minus 1, it will get from the I minus first position to the I position. So therefore, the length can be at most I minus 1. So Ri, the length can be at most I minus 1. And because of observation 2, if Ri has length 1, the previous line implies that Ri has to be exactly S of I minus 1. Because it has to end with S of I minus 1. So it is only this is possible. So now we are ready to describe our involution. So for a permutation, like you first get the canonical reduced word decomposition and you find the rightmost Ri plus 1, say Ri naught plus 1, which has length greater than or equal to 2. The one to its right has to have length 1 or 0 because we are looking at the rightmost one with length 2. So this is forced to be length 1 or 0. If it has length 1, then we know it has to be exactly Si naught minus 1. If it has length 0, that means it is 1. So our involution will do the following. It will flip Si naught minus 1 to 1. And it will flip 1 to Si naught minus 1. So if there is no such component of length 2 or more, then we will just leave the permutation fixed. This is our involution. So in our example, where we took the permutation to be 4, 1, 5, 2, 3, like this canonical reduced word decomposition was S2, S3, S3, S4, S2, S3, 1, S1, 1. So here S2, S3 is the rightmost one with length greater than or equal to 2. So you look at the one to its right, which is 1 here. So 1 which is R3. So we will flip what is there in R. So from 1 we will make it S2. So this gives us a new permutation. Like so 5, 1, 4, 2, 3 will be this involution. And this gets the job done. I have not included the details. Like you can, like this paper appeared in the Journal of Algebraic Combinatorics in October. So like, you can take a look at this one. So now like we've seen 4 things. We've seen the descent polynomial. We've seen the sign descent polynomial. We've seen exceedance polynomial, which is the same as the descent polynomial, and we've seen the sign exceedance polynomial. So now we are going to look at some parallels between results for the Eulerian distribution over Sn and the corresponding like result for the distribution of descents and exceedance over An. So gamma positivity is something that the Eulerian polynomials satisfy. So what is gamma positivity? The sequence is said to be gamma positive. The sequence can be written as a Z linear combination of the rows of the Pascal triangle, adjusted so that their center of symmetry is matching. For example, 1, 26, 66, 26, 1. This was a fifth row of the Eulerian triangle. This can be written in this way. 1, 4, 6, 4, 1 is a row of the Pascal triangle. 1, 2, 1 is a row of the Pascal triangle. 1 is also a row of the Pascal triangle. And with this linear combination, we can get exactly this one. So every palindromic sequence of positive integers, one that reads the same from front and back, can be written in this way. So this requires some argument, but one can convince oneself that this can be done. So a polynomial is said to be gamma positive if the polynomial can be written as a okay, there's a small typo, n linear combination of polynomials of the form t power j 1 plus t power n minus 2j. So this t power j shifts the center of symmetry of the binomial, like 1 plus t power n minus 2j, so that they all match. So this is a theorem of Forta and Schutzenberger, that the Eulerian polynomials are actually gamma positive. So they can be written in this basis, this t power j 1 plus t power n minus 2j, n minus 1 minus 2j with positive integer coefficients. And we know a nice description of these coefficients also. So over an, what can we say about the descents when we look at them just over an and not over Sn? So an plus we will be the descents looked at over an minus will be the descents looked at over Sn minus an. So the problem here is that for all n, these polynomials are not palindromic. This is slightly disappointing, yes. However, whenever they are palindromic, they are gamma positive. So the polynomials an plus and an minus are gamma positive if and only if n is congruent to 0, 1 mod. And they are also gamma positive with the same center of symmetry. That is, for each n, an plus and an minus share the same center of symmetry. So additionally, in this reference 2, like they ask, okay, so what, when it is not palindromic, can we say, like, is there, like, how can we write it as a sum of gamma positive polynomials? Like, how many gamma positive polynomials summands do you need to write this, like, with different centers of symmetry? Like, how many different centers of symmetry do you need to write? And they found out that the answer was at most 3. For n congruent to 2 mod 4, it was 2, and for n congruent to 3 mod 4, it was 3. The number of centers of symmetry is required. So for exceedances, so here also we run into the same problem. It is not palindromic. These polynomials are not palindromic for all n. However, for all odd integers, these polynomials are palindromic. And for odd integers, they are also gamma positive with the center of symmetry n minus 1 by 2. So another additional properties that the Eulerian polynomials or Eulerian numbers satisfy is that the sequence is log-concave for k, like of fixed n, that row of the Eulerian triangle is log-concave. So what is log-concavity? A sequence of reals is said to be log-concave if for each I we have this following relation: ai square is greater than the product of ai plus 1, ai minus 1. So typically there are a few methods to show that sequences are log-concave. Like, one of them is this theorem of Newton, which says that if you have a polynomial with real roots, its coefficient has to be log-concave. This is one way of getting log-concavity. But okay, so there is this additional n choose k term over here. So this is something called ultra log concavity. says that a sequence is called ultra log concave if the sequence AK by n choose k is log concave. So sequences that appear as coefficients of real rooted polynomials are ultra log concave by Newton's theorem. So before we talk about log concavity, let us just take an aside and look at real rootedness. So Frobenius proved that the Eulerian polynomials have only real and simple roots for all natural n. However, we do not know the counterparts of this result for the descent and exceedance distributions over A. These are conjectures. So the descent polynomials over an and Sn minus an plus and an minus are expected to be real rooted for all n. I believe they say that they have verified the conjecture up till n equal to 30. Fulman, Lee, Peterson, and Kim. And this is my conjecture that the exceedance polynomials also behave the same way. They are also real rooted. However, for n strictly greater than 5. For 3 and 4, they are not real rooted. They have complex roots. And this also I have also verified up till 30. Like it's harder and harder to verify this. And like till 30, I was not able to get any like complex roots. So I think this is, I believe that this conjecture is true. So again, I will also give something that I believe supports this conjecture. So because of these conjectures, we do not have use of our the theorem of Newton to get log concavity of the exceedance numbers and descent numbers for an. We do not know them. So we have to go through a different route. So while trying to prove this, we ended up proving something stronger. So let A be a sequence, let A and B be two sequences. Then let S of A comma B be the set of 2 power n sequences that are formed where each CK is one among AK, BK. For example,
Umesh, are you there?
Yeah, he freezed for me too.
Yeah.
Ah,
Can you write
Yeah,
chat to him?
sure. Write to him immediately, but hope he will get back.
Yes.
Maybe it's the internet, I don't know.
Yeah, in India, it's very far. Oh, he disappeared. Maybe I come back.
Okay.
Hopefully. Yeah, sorry about that.
Yeah.
It's very early in the morning for him or late at night.
Is he back? No. Yeah, he's.
yeah, can you hear me? Sorry, like there was a power cut and the router just restarted on its own. And I lost internet for a second.
Okay.
Welcome back. You fixed it?
Yes, sir. Thank you. So let B and K, yeah, I'll just continue from where I left off. So let me maybe, yeah, so S of A comma B is the set of 2 power n sequences. And if all the sequences in this are log concave, then we will say that A and B are strongly synchronized. So this is the result. So B and K is the number of permutations in A n with K descents. C and K is the number of permutations in Sn minus A n with K descents. P and K is the number of permutations in A n with K exceedances. Q and K is the number of permutations in Sn minus A n with K exceedances. So we have 4 sequences. So all 4 sequences, like all 4 power n sequences that can be formed with these 4 sequences they are all ultra log concave. So this is my result. Like, so when you just look at these 4 sequences in particular, they are ultra log concave. So I mean, if these polynomials were real rooted, we expect these coefficients to be ultra log concave. So we have shown that they are ultra log concave. So this is in some sense supporting the real rootedness of these polynomials. So now I want to take a look at some pattern avoidance results for the alternating group. So first we have to define what a pattern containment is before we can define what avoidance is. So given a permutation tau in Sk, a permutation pi is said to contain the pattern tau if there is some sequence I1 lesser than I2 lesser than so on lesser than Ik such that pi I1 so on till pi Ik is order isomorphic to tau. So here is an example. So 24153 contains the subsequence 413, which is order isomorphic to 312. So therefore it contains the pattern 312. However, the permutation avoids 321. So pattern avoidance means that if pi does not contain tau, we say that pi avoids tau. We will denote the set of permutations in Sn that avoid tau by Sn of tau. For example, the number of permutations in S20 that avoid the pattern 213 is the password of a Zoom meeting. So we will define what Wilf equivalence is. If for 2 patterns, sigma comma tau in Sk, if the cardinalities of Sn sigma and Sn tau are the same for all natural numbers n, then 2 patterns are said to be Wilf equivalent. We will denote it by sigma is equivalent over Sn to tau. For example, all 3 length patterns are Wilf equivalent. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 3, 2, 1. All of them are Wilf equivalent. So we are going to imitate this to look at the counterparts of these results for the alternating subgroup. So we will imitate this definition. Let us look at only the permutations that are there in An, and let us look at the ones that avoid sigma and avoid tau. We will say that 2 patterns sigma and tau are even Wilf equivalent if like these 2 sets Sn sigma intersection An and Sn tau intersection An are equal. So this was proven by Simeon Schmidt that there are 2 distinct even Wilf equivalence classes for patterns of length 3. Whereas we saw that there was only 1 over Sn for patterns of length 3. For length 4, Jaggard and Baxter actually completely classify the Wilf equivalence classes. There are 11 even Wilf equivalence classes for patterns of length 4. There are only 3 for like over Sn, but there are 11 over here. So for 5 and above, there is still some uncharted territory. So we know that the even Wilf equivalence classes can be anywhere between 35 and 39, depending on the veracity of these conjectures. So the following equivalence hold. This is the conjecture of Jaggard and Baxter. It was given, I think, in 2000. I don't know, 2009, 10. Like the main problem, like if you look at, for example, the third equivalence in this 1, 2, 3, 5, 4 and 4, 5, 3, 1, 2, they're actually just the reverse of each other, right? But this is somehow trivial over Sn. Like over Sn, it is trivial that if like sigma is a pattern, then if you reverse the pattern, like this is Wilf equivalent. However, over An, it is not that simple because reversal need not preserve the sign. So it is slightly tricky in this situation. Like, so these we do not know as of now. So, and yeah, so over 6 also we do not know, like they give an exact lower and upper bound for how many classes there can be. So 6 also there are some classes which we do not yet know. So
Umesh, at
yeah,
which year were these results proven and these conjectures made? How recent is this paper?
no, this paper is quite old. Like I will say around 15 to 16 years, somewhere in that ballpark. And it's quite
Okay.
old. Yeah. So and it has not. I've checked. Like I checked on Maths in it yesterday. It has only one citation, and that is also like it's not something that builds on this work. Like it is just referencing that this work exists. So like these are, I believe they are open. Like, one has to ask Jaggard and Baxter. They're still open, but yeah, at least they're open. The paper is pattern avoidance by even permutations. That is the paper. It appeared in the Electronic Journal of Combinatorics. So over 6 also there is a partial classification. A lot of them are known by what is this prefix reversal. Like a version of this exists for AN also. So a lot of it is known, but there is still some things that we don't. So the more surprising conjecture is this. Like it's in some sense it is not surprising. Like we expect this, but like it is surprising that it remains open. That is why it is surprising. Like if sigma and tau are even Wilf equivalent, then sigma and tau are Wilf equivalent. That is, the conjecture asserts if the number of even permutations avoiding sigma and tau are the same, then the number of odd permutations avoiding sigma and tau are the same. So, this seems to be the case. They said that they have verified it for quite a few values. I don't recall exactly how many. So like this is the here this is exactly since it's a experimental maths. These are experiments that I've just run and I just come up with some conjectures that I just observed. So can we generalize the results that we have seen somehow? Like we looked at some gamma positivity results, some real rootedness conjectures. So one way to generalize is this. The permutations in AN are the permutations in SN whose number of inversions are zero mod. They're even number of inversions. So what about the permutations whose number of inversions are zero mod Q? Like the problem once again is that palindromicity is not available. So that is a problem. But like as far as evidence goes, like it seems that whenever these polynomials are palindromic, they end up being almost. So like we can ask that like are these descent enumerating polynomials over these classes, are they palindromic? Are they gamma positive? Are they real rooted? We can ask these questions for K. And here is a concrete conjecture. So if you look at the ones for 3, if you just look at the number of permutations in SN whose inversions are 0 mod 3, then for all n of the form 0 and 1 mod 3 and n greater than or equal to 4, the polynomial appears to be gamma positive. Like when you count descent over this particular set of permutations.
Did you try to test it on a computer for?
Yes, sir. Like as far as I could, I have tested, sir. But like,
Beautiful conjecture.
so like, and like 3 is just something that like I tested for a while. Like you can 4, 5, 6, like, and it seems to be the case that whenever you end up with a palindromic polynomial, this appear like comes from some like uh, condition on n mostly, a condition on n and the number of in like whatever is inside this modulo. So you can come up with cases where it will always be palindromic. Like it is some like for each n you can find some k such that like it is always palindromic and those appear to be gamma positive. So this is something that I just noticed. I currently have no idea how to prove this. So these are my references. I think, yeah, back it came in 2012. Yeah, it's 12 years old.
Okay.
This
Well,
was,
yeah, go ahead.
Well,
Do you have
thank you.
anything more to say? Yeah, let's thank the speaker, yeah, and for
Thank
the
you.
interesting
Yeah, thank you.
results shared. And let's open the floor for questions. We have plenty of time.
Yeah, so this last conjecture, where we do it mod 4 or mod 5, it still seems to be true. Do you try?
Yes, sir. It seems to be true. Like, yeah, but not
Yeah.
for these particular n. Like, if you
Ah,
modify the n, like, I think here for 3 it is 0 and 1. Like, if you
yeah.
change here, if you change it to 4, then it changes appropriately. N also changes appropriately. And you still have some palindromic polynomials, and those turn out to be gamma positive for small values at least.
I see.
And speaking of the same conjecture, if n gives remainder 2 mod 3, then
Yeah,
is it true
it is
that
not
that's
palindromic. It is
sometimes
not palindromic. Like, it is never palindromic. Like, so, like,
but
that I think we can.
sometimes could it be the case that sometimes it is palindromic and then in that cases you get gamma positivity or no?
These I do not know, like, if they are palindromic. Like, at least the ones I've checked, like, they're not palindromic. So, but yeah, these are the ones that are palindromic for at least if we set 3 here, like mod 3, if we look for inversions, then these are the n for which it is palindromic. Yeah, there, like, I have some other things, but they were not as concrete as this. Like, they were still just like a lot of data, and I had to sift through it and come to some conjecture. But like, I had not done that, so I just wanted to present this.
Okay. Any other questions for Umesh?
Do you have a thing of interfacing it with other statistics like the major index?
So one thing, okay, maybe this I can mention. Uh, uh, let me go back. I think it's better to explain. So if you look at this theorem, so A and T, which is the Eulerian polynomial enumerating descents, like we have this gamma positivity result. So if we look at A and T comma Q, where Q is keeping track of a major index, then there is a like theorem due to Zikong Lin, Guan Yu Han, and I think Zheng, like Jiang Zheng, that says that there is a Q gamma positivity that appears. Like there is like the definition is slightly complicated, and I cannot recall it from the top of my head. But so there is a Q gamma positivity that happens,
I see. So it's
and
like,
that seems to be the case for this also. Like for n is congruent to 0, 1 mod 4. If you look at an plus t comma q and an minus t comma q, where q is keeping track of major index, then these also seem to be like q gamma positive for these
I see.
two
So
indices.
you can stick a Q there. That's nice.
No.
Thank you.
These was something I noticed. Yeah. Otherwise,
All
I'm
right.
not sure how to like include more uh, talk more what I mean, like other statistics into this, like how to do it. I do not know.
Yeah, beautiful.
Yeah. Are there other questions? Um, If not, Umesh, you're welcome to email me or Dr. Zida Sweitz.
Yeah, please
And,
email me the slides. But go to bed first, and after you wake up tomorrow, then you can email me the slides for posting.
Yes. Yes.
And Stoyan will send you a link to the recording once it's
Yeah.
available.
Yes.
Yes.
Okay. Thanks everyone for staying.
Thank you.
And
Yeah,
to
thanks.
Umesh.
Yeah,
So,
good night.
yeah, good night and yeah, see you next time.
Yeah, thanks.
Bye bye.
Thank you.